Okay, this is video 26.2. In this one we're going to look at calculating the capacitance for a general capacitor. We looked specifically at parallel plate capacitors in the last video. Now we're going to learn how to do it for a spherical capacitor. And generally when you're faced with a capacitor that isn't a parallel plate capacitor, you're going to assume that you have charges of plus Q and minus Q on the two conductors. That's easy. Next step is, based on those assumed charges, you calculate the electric field in terms of Q. So this is going to be done symbolically, and usually you'll use Gauss's law here, because capacitors, whether they're cylindrical, spherical, or parallel plate, usually are designed with a high degree of symmetry. And I just realized I misspelled calculate. Oh well. Once you have the electric field, you're going to calculate the potential difference from the field, and you're going to use the equation delta V equals E dot ds. Now for a parallel plate capacitor, the electric field was uniform, and so it's just simplified to the field times the distance. But in spherical and cylindrical capacitors, that won't be the case, and you'll actually need to evaluate the integral. And then once you've got that, you'll use C equals Q over V. The result is that the Q's are going to divide out of the equation, and you'll be left with the permittivity constant, epsilon 0, times some quantity with units of length. In the case of the parallel plate capacitor, that was the area divided by the distance. Area is in square meters, distance is in meters, so that works out to be something with units of length. And another way of writing the permittivity constant, units, is farads per meter. If you don't believe me, actually even if you do believe me, try showing that based on the units you know, the Newton meters per coulomb squared then. Now we're going to look at a spherical capacitor. What it is we've got a central conducting sphere of radius little a surrounded by a spherical conducting shell of radius little b. You're going to put plus Q on the inner shell, minus Q on the outer shell. There's our first step. Our next step is we need to find the electric field between the two shells. And you can just figure out from symmetry that the electric field points radially outward, and we want to find out what it is. So we'll draw a Gaussian surface of radius little r, and we'll use Gauss's law, which says the enclosed charge divided by epsilon 0 equals the total flux. Now the enclosed charge is easy, it's just plus Q. Notice that the the outer shell is entirely outside, so we don't care about the minus Q for this part of the calculation. And that equals the flux, and because the electric field has the same value at every point on that surface, the flux is just the electric field times the surface area of that Gaussian surface, 4 pi r squared. And so the electric field works out to be 1 over 4 pi epsilon 0 times Q over r squared, which looks kind of familiar. Now though, what we need to do is we need to find the voltage difference between the inner and outer shells. So we need to integrate starting here and ending up there. And so delta V is going to be the integral of E dr, because we're moving along the radius. You're moving from radius little a up to radius little b. And so we bring all the constants out the front of the integral, and that leaves us with dr over r squared integrated from a to b. That's a very easy integral to evaluate it, and it's q 4 pi epsilon 0 negative 1 over r evaluated at a and b, so that works out to be 1 over a minus 1 over b, which you can write as q times b minus a over 4 pi epsilon naught ab. We're not quite done though. Our last step, we're going to find the capacitance, which remember is q over v. So we've got our expression for v, and we'll go to the next page for this. Oh, no we won't. I will make this all a wee bit smaller. So equals q over all of this. Whoa. That's better. And this works out to be 4 pi epsilon 0 ab divided by b minus a. Probably not really worth memorizing that expression, but you may be asked to derive it on an AP test, so remember that basic procedure. The hard part is usually finding the voltage from the field. And now on the last page, we're going to look at what happens when A and B are very similar. In other words, you have A that is almost B. So the difference, A minus B, we're going to call D. And that is much, much smaller than A and B. Now if we look at that expression, 4 pi epsilon 0 AB divided by B minus A. Now B minus A is just the distance between the two shells D. And notice that A and B are very close together, so you might just say that A is approximately equal to B, which is approximately equal to another quantity that we'll call R. And so this works out to be 4 pi r squared epsilon 0 divided by D, and 4 pi r squared is just the surface area of that sphere. And so for the case where A and B are close together, the expression for the spherical capacitor actually results in the same equation as a parallel plate capacitor, just in this case the plates are bent into spherical shapes. Keep in mind though, this is only true when A and B are close together. So after this video, you should know how to calculate the capacitance for a general capacitor, the 4 steps in the first slide, and you should also especially be able to get the capacitance of a spherical capacitor. Tomorrow I'm going to be checking question 1 and problem 5.